learning would go. Was anybody here in the talk about delivering deep learning that I gave a short while ago? Okay. Oh, goodness. Okay. So just so that you don't feel cheated, the first half of this, which talks about kind of getting you up to speed on deep learning, is literally the same content. So in the previous, and so if you wanted a chance to look at something else or come in or take a little bit longer, I just wanted to let everybody know, because there's kind of two phases. There's the what is this thing we're talking about, and then there's the I'll say Go specific, but it actually applies to other languages too. If you're a Java developer, a C# developer, a Ruby developer, a lot of the things I'm going to talk about actually would apply to you as well, if you're not strictly Python and C++ and such. So, but this will be in the context of Go. So if anybody wants to skip a few minutes, feel free. I won't be offended. You can walk out and pop back in just a little while, and that way you're not seeing the same content over again. So, but I hope you'll come back for the second half there. There you go. I just didn't want you sitting back there going, why am I here? So go ahead, and I have my little remote here, so pardon me for looking. I'm not ignoring you. I'm actually looking at what's on the screen here without going. So I'm Chris Benson. I am the chief scientist for AI and machine learning and deep learning at Honeywell. Specifically, Honeywell has four what are essentially global divisions. We call them strategic business groups. But what mine is, it's called Safety and Productivity Solutions. And we have tons of different product lines in there, and everything from robotics to speech recognition headsets to printers, scanners, a lot of industrial equipment. And my job is to apply AI general technologies to these different product lines to enhance products or create new products that don't exist, that are driven by it, where value can be added. And so in that sense, I have a lot of very hands-on pragmatic experience with deep learning. It is the core of my job. I've also worked previously at Accenture as an artificial intelligence delivery manager. Wasn't there too long, but it gave me a different perspective on going to different clients with these technologies and understanding how we can meet their needs and stuff. The two jobs actually are not that dissimilar in a lot of ways. I also do a lot of strategy in this space in terms of how do we, at Honeywell, to give you a sense, last night I was on the phone with my CTO. I was coming home from the airport. I'd spent this week in Pittsburgh, and so I haven't been able to attend. Little side, everyone enjoying the conference? Pretty good. I have not been, those who were in the last one, I had just arrived beforehand, so I have not actually had the chance to enjoy the conference like everyone else. So I got off the plane last night, and my boss at 7 p.m. gave me an assignment which took me to midnight on strategy, and then here I am today trying to get the last bit of this in. So we do a lot of strategy, and then I have I have multiple teams that actually try to go out and do these things that we are strategizing, and I do it myself. I'm a hands-on engineer. Been a software engineer for 25 years. And I do a lot of architecture for this. Obviously, public speaking on this space, like what we're doing here. Has anyone here ever attended the Atlanta Deep Learning Meetup? You have, sir? You have? There we go. We just have a couple. So that's here in town, obviously. We have a community. We have 1,300 members that are interested in deep learning, and it is a very popular meetup, and I can say because we actually have 60 to 80 people show up on any given month's endeavor. So that's a lot of people that are interested. It's, when I started it at the beginning of the year, and I was like, the first one, I was thinking maybe 5 people will show up if I'm lucky, and 60 people showed, and I was like, wow, this is pretty amazing. So it's really catching on. A lot of people want to know about the technology, and that's a great way to get started or continue or make connections with companies. There's a lot of academic to big company to small company connections that people make there. Before it was called deep learning, I got introduced to deep learning in 1992. I'll talk about that in just a moment. I'm just really into futurist. I'm very optimistic. I love talking about these great technologies. I love seeing what's next. But I've been doing this for a while. My first Hello World was IBM Basic using this. Anybody here remember this? It was the original IBM PC. So for a guy in his late 40s, which is where I'm at, my parents are actually computer people, and at both Lockheed and at Georgia Tech, my mom taught in computer science. So that was kind of the weird kid whose did this, nobody else did that. Usually it was the kids that were the new ones doing that in their house. So I had an early start. And then this is what I work on these days. And does anybody know what that is other than this? It's a DGX-1. It is the world's first and fastest AI-specific supercomputer from NVIDIA. A bunch of the latest versions of NVIDIA GPUs in it so that you can do training, which we'll talk quite a bit about in a few minutes on that. Okay. So I was introduced to this topic 25 years ago. And here in Marietta, Georgia, just north of here, is a giant Lockheed plant, and that's where the F-22 Raptor was created and engineered from concept all the way through to production. And it was, to this day, it's still the world's leading air superiority fighter. There might be some competition at some point, but it's a pretty amazing aircraft, and I've seen it in person multiple times. And so they had quite an issue, though, back in 1992 at Edwards Air Force Base when they were testing it, and that is that the test pilot was supposed to be trying to crash the plane on purpose because the plane's avionics were supposed to prevent that from occurring. And so, see if this will work. He's trying to crash it. The avionics are stopping. Oh, avionics didn't work. It hit the runway. Pilot was okay, but he slid quite a ways down the runway there, and that was a really bad thing for the United States Air Force. They had 2 prototypes. And with lots of money invested in this, and one of the 2 is now destroyed. Pilot got out safely, but Lockheed is like, how do we get to fix this? So they assigned it to some folks to deal with, and there was an engineer who was really focused on bleeding edge technologies. Neural networks of the day was one of the things he was interested in, and he ultimately, long story short, applied neural network technology and got through that problem. That was my dad. So what I used to do as a kid is I was a college kid, and I would come home, and he'd come home, and we'd try to spend a little family time together, being apart all day. And I got an introduction into advanced neural networks that way. It wasn't my interest. That's not what I was doing in school, but I learned a lot, and I got a passion for it. And then it kind of, that problem moved on. He moved on to other things, and it went away. And then as deep learning came roaring back in over the last decade, I got an interest again in it, and so here I am today. So let's talk for a few minutes. I'm going to go fairly quickly because we have a shortened time session here. Feel free to ask questions, and if it's right on, then I'll try to answer it quickly, and if it's not, then I'll try to deal with it either toward the end if we have any time remaining or with a one-on-one afterwards. But it's hard for me to talk about Go in deep learning if you don't have a good sense of what deep learning is. Quick show of hands. Who here feels they have a bit of expertise in how deep learning works? Who's pretty solid in that? Okay, there's a few. So if you know that, you can go to sleep for a few minutes and it's fine, and I won't be offended, or if you want, it's fine to hop up and walk out if you understand like backpropagation. But I'm going to run through a quick tutorial for everybody and then talk about how Go fits into that. And so feel free to do that. So deep learning is modern artificial intelligence that works today. It's the approach to machine learning that is driving the current artificial intelligence revolution. Basically, all these things that you see on CNN and just not even technical news sources, but like TechCrunch or something, but even mainstream, most of those things that rise to the interest level where people are going to want to do them are deep learning driven, one way or another, with different types of architectures. And there's some quotes in here that I talk about, and I'll address what book this is later. But I have several quotes because they kind of get it right down. Deep learning is a type of machine learning where you're kind of taking statistics and kind of modeling how people's brain works to some degree, and that's a very loose sense of the word modeling. It's more of an inspiration. Hey, the brain kind of handles it this way. Maybe we should research that. And they try to find ways along with applied math of solving problems that way. And it's a very specific way of approaching a complex problem. So it's an approach to AI that allows computer systems to improve with experience and data. And it's a lot of data, and we'll talk about that. And you're learning from data without explicit programming. So I'm not a data scientist by background, actually. I have a lot of data scientists, data science, PhD types that work for me, but I'm a software engineer. I'm a career software engineer. And so I've spent my career, regardless of what the project was, web or embedded or system, whatever, basically doing lots of, if this, then that, and case statements, and trying to figure out all those things. Think of all the times, run it again, oh crap, crashed, and I'm gonna keep thinking of every possible thing I can. Finally, it's passing QA, it's passing all my unit tests and my integration tests, and I can put it out. This is a different approach from that. You're not trying to solve for everything, because when you scale up to big problems, it's really hard to do that well without bugs. So what we're basically doing here is we are trying to go for a way where you can learn and generalize from data. So you gather knowledge from experience, and then you're able to formally specify what the computer needs to know so that it can train itself. So deep learning is the modern application of deep neural networks to achieve machine learning. And I would argue to some degree it's a rebranding. It's the natural evolution of neural networks, but it's not something different from. It's just taking neural networks, making them better, do architectures and stuff like that, and making deep. And we'll talk about what deep means in a few minutes. But they're essentially synonymous. So this is kind of how it fits into the ecosystem. There's other things in machine learning that are not deep learning, but deep learning is kind of the big power hitter these days, and it's certainly getting all the hype and the buzz out there. There's very little, if anything, in my view, and this is debatable, that's AI that's not machine learning or deep learning specifically. So I would argue with somebody who said, "Oh, I'm doing AI, but it's not machine learning." I don't think that's I would be very curious to understand what that is. So, and in a broader sense, deep learning sits at this juxtaposition. You have those two. This is basically the old graph that you just saw, and I've added in on this side big data and data science. Deep learning is a field that sits right where a bunch of fields touch each other, and you really need all of those. It's a multidisciplinary field to take it out and make it practical and put it into production. And this is just another timeline, kind of saying, over the years there was kind of the old AI, which is no longer with us. Nobody cares about that anymore. We kind of moved into machine learning, which kind of evolved into deep learning over time. So in recent years, there's been all this growth, and really that's come about. My dad was successful in the 90s with the plane that I showed you, but that was a rare thing because most people did not have successes in that day and age. And the reason is they didn't have enough data, they didn't have enough computing resources, and frankly, the algorithms of the day were quite limited compared to what we have available today. And so he was lucky. He was at Lockheed. They had tons of computing resources for the day there. He tried the different tools of the day, and he actually, what solved it, and I couldn't relay, I don't remember the specifics, actually was something of his own. It was a neural network architecture that he came up with by himself. So it's not out there and published. And then, frankly, just not enough data. But when they were trying to solve the problem, they would fly the F-22 around, and they were bouncing it Edwards. They had a test pilot flying it. They had sensors all over the plane, and those sensors were taking the data, bouncing it to one satellite, bouncing it over to another, and then down to the Lockheed plant. So they were kind of generating big data on their own in 1992 through kind of a unique circumstance, but that wasn't available to most people. So he had some advantages that we haven't had until very recently. So now we have cloud computing, and so suddenly we have a massive amount of computing capability available to us. Lots of data sets, we have more data than we know what to do with in many cases, and the development of the algorithms and the architectures of deep learning have advanced significantly over the years, especially over the last 10 years. There was kind of a winter for deep learning between about 1995 and 2005, roughly, but then it came surging back right around, I think it was 2007, if I'm remembering the date correctly, so over the last 10 years. So why does this stuff matter? Well, we all hear about Google's self-driving cars. We hear a lot about chatbots. When I was at Accenture, I was so sick of hearing about chatbots for our customers. It was just like, oh my God, there's so much more you can do with this technology, and all we can talk about are chatbots. So it's a pet peeve of mine, chatbots. So please don't ask me any questions about chatbots. There's a lot of use cases, and this barely scratches the surface. There's so many things that you can do, and this is just limited by what the slide can hold, and there's really too many words here anyway. Basically, by line, you're talking about security, you're talking about marketing, computer vision, speech recognition, transportation, healthcare, and finance. And there's many other fields I'm leaving off, and there are many use cases within these fields that I'm leaving off. But that gives you a little smattering. Andrew and Guy put out this recently, and I just added it last night to the deck, just because it was another way of looking at, it's how he looks at it when he's looking at machine learning and deep learning specifically. And he says he has an input, and he's looking for a particular response, and he's kind of saying, what is that application? So I put it in there just as another perspective on it. So this is a pretty interesting thing to me. Deep neural networks can precisely approximate any continuous function. And if you're not a mathematician or a statistician, that is the most boring sentence you have ever heard. And most people, they kind of see that in an article or a textbook and they gloss over it unless they understand the implication. But I read a lot of stuff and I kind of saw that a few times and didn't get it. Remember, I'm not a data scientist by background. I'm a software engineer, so I was like, yeah, whatever. But that's the magic right there. The reason that you see neural networks being applied to so many complex problems is that right there basically means if input, then output, and really anything you can think of. There are exceptions, there's edge cases, but there's so many things in the world that can be represented by continuous functions. And so if you're looking at your life and things that we do that are meaningful to us, and you say, how would I kind of put that into an algorithm? Or maybe I'm using a device which is using algorithms quite literally and stuff. There's all these functions that do this and do that, and there's a range. How hot is my coffee? How hot, how cold? And that you can represent that way. And so there's so many things in the world that can be represented by continuous functions, and we have this toolkit that says, hey, if it's a continuous function, you should consider applying me to it. And if some of your other tools in your machine learning tool belt aren't quite sufficient or giving you as much as you want, this might be something to do. And you know what? That's a huge statement, because you're saying that this deep learning toolbox is sort of a universal toolkit. It's not to say it's perfect. It's not to say it applies to every problem in the world. It's not the panacea. It doesn't create world peace. But it's a really, really flexible set of tools that is at least worth your consideration if it is a capability that you have. So we're really saying that deep learning is a universal approach to solving complex problems. It's not the only way to solve them. There might be cheaper, less time, less cost ways of doing it. There are a lot of machine learning algorithms that might suit your problem just fine without the investment in this. But if they're not meeting your need, maybe this is something that you want to look at. So right now, this is happening throughout the industry. This came about a year and a half ago. The Google CEO basically said, we've been building this mobile first world for the last year, and you heard mobile first from every company on the planet for so long. And he kind of got to a point where he's like, okay, we've done that. It's assumed that you're mobile first. Mobile is not the thing you should be talking about now if you're still out on the leading edge of doing stuff. You're playing catch up if you're talking mobile at this point. So he basically said, we're already doing AI, but we're really going to invest, and we want to go across all of our products and services and see where it makes sense to apply these things. And so he's talking about shifting, and this is an ongoing thing now. This is not new. And so they have been going around and doing exactly that. And it's all the way from obscure back-end algorithmic problems to front-end user interface. Here's Google right in front of you, and how does the user interface itself react to you? All these things are being driven in part by deep learning approaches, and that is it's common throughout Google, and it's really common throughout most companies. As the guy who drives AI for my strategic business group at Honeywell, that's exactly what we're doing. It's exactly what every player who's not fallen far behind is doing right now. So you will certainly consume AI. You will sorry, as I move around, the sound changes a little bit. You'll certainly consume AI, and you may very well be creating AI and machine learning microservices going forward. And there's a lot, I say microservices, there's a lot of crossover these days between DevOps things in production. Things like Docker, if anyone's familiar with that in terms of how you do it. We can talk a little bit about that later. And a lot of those things that you're doing will be based on deep learning in the years going forward. This guy is a CIO, and I was not familiar with him before I read the article. You may be already. But he's saying something that's really important. And I don't know that his details are exactly right, but the underlying idea is really important. And that is, he basically saying, if you got into this stuff before now, a little ways back, then you're going to invest a lot of time and money and effort and get a very limited return because we weren't quite there yet. And he's saying, but if you wait the same amount of time on the other side, you're going to be hopelessly behind because everyone is doing this thing. We're in that sweet spot, and the cost of doing deep learning can be very expensive, but depending on what you're tackling, relative to the past, it has dropped significantly in the last 2 years in particular. And so this is the time, whether you're a 3-person startup or whether you're a Honeywell, to get into this space and be doing this, because your competitors are doing this if you're not. And so there's a little bit of pain, there's going to be some wasted effort, but if you're not trying at this point, then you're going to be chasing constantly as people surge forward. Not my favorite person in the world, a little biased on my side, but he said this on September 1st to a bunch of university students in Moscow, and he's basically saying, go do AI, because that's how we're going to be, what we are, in the world. We're going to be a power, and it's going to be based on this. And so with world politics being what they are, everybody's going to be doing this. Whether you're doing it or not doing it, this is something that people are investing in. Investing a lot. Investing here, we invest millions and millions, and in China, we invest billions, literally. In another talk later on today, I'll talk about that a little bit more as well. So I had to throw that in, I'm sorry. Not trying to make a political statement. So I want to point out, so as we get into what is, very specifically, what are neural networks, this is something out of the textbook that I mentioned that doesn't mean a lot to people when they first see it. But it's basically saying that you have a hierarchy of concepts and you're building more relevant concepts out of simpler concepts. And we'll talk about what that means going forward. And so you're basically having this graph of concepts that build upon each other to give you contextual meaning. And so how does deep learning actually work? I like this because I'm ready. Let's do it. Hands in. Training enables generalized predictions using known correct results. And what that means is that you have a bunch of training data, you're not memorizing the results in your training data. You're not saying, oh, I have a labeled data set. It's called supervised learning. I have a data set that I'm going to learn off of, and I'm going to say, oh, I've memorized that one, I've memorized that one, I've memorized that one. Because you can memorize all those, but if you're memorizing, then when you get to something that's new, you go, I don't have that. What do I do? So the point in deep learning is to create generalizations so that if you go through 10 million examples on a training set, that when you get to the next 100 after that you've never seen before, it can make an accurate inference, an accurate prediction on something it has never seen before through this training. You are generalizing the knowledge. There we go. So, and it takes lots of known correct results. That's the one thing that people, if there's one thing I have seen over and over again that trips people up as they get into deep learning, it is that. And I'll talk a little bit more about that later as well. But with a lot of machine learning techniques, you need a data set to do some stuff. But it doesn't, by today's standards, it doesn't necessarily have to be a huge data set. When you get into deep learning, it's expecting a lot. And that's one reason it didn't work until recent years when we had such huge data sets. But a complex problem might be 10 million records that you're going to iterate through of highly relevant data to what you're trying to deal with. A small one, I saw a very small demo that we did in Honeywell. It's a good demo on noise cancellation. And they only used, the engineer only used 80,000. But that was kind of a toy demo. It was to show a proof of concept. He worked on it for a couple of weeks, that kind of thing. But 80,000 is ridiculously low for most real life things that you're going to do. So that gives you a sense. If you don't have that data available, that's one thing that you need to be thinking about. So once you're trained, you can take these generalized predictions from the new inputs, like what I said a moment ago. And that allows you to learn from experience. And you're defining these concepts in terms of the simpler concepts, like we said. And we're just about to show that right here. So this is a toy, truly a toy neural network. It's tiny, it's technically a deep neural network, and that's defined by the number of hidden layers. According to the textbook definition, if you have more than one hidden layer, and I'll show you what each of these layers are in a second, you're a deep neural network. But nobody would consider this to be real in the world. It's just for explaining. I have an input layer, I have a hidden layer, a hidden layer, a hidden layer, and an output layer right there. And so I have 3 hidden layers, so it's a deep neural network. But in real life, this might have 5,000 layers that are hidden in it, and each of those layers might be 10 to 50,000 features, going into it as the layers vary in size and such. So you can have, so if you think about just start doing the math and multiplying those out, that's a lot of computation that you're doing. The computations aren't necessarily sophisticated, they're simple, but you're doing it at such scale that it requires a lot of resources, which goes back to why we need cloud up until now and other such things like supercomputers. So this is what the inside of each of those neurons looks like. You have the inputs coming in. They're fully connected from layer to layer. So on any given neuron, on any given layer, it's on a feed-forward network, which is what we're talking about, because there's a particular use case, which I'm about to identify, that we're doing. Every neuron on that layer is connected to every neuron on the layer behind it and the layer in front of it. It's called a fully connected feed-forward network. And inside, it has, it basically aggregates all those inputs, and then it runs them through an activation function, which gives it its nonlinearity. It basically, there's different algorithms you can use. They're all very simple, but it allows you to say, how much do I care about the inputs? How do they aggregate out? Because this is going to get mixed in with all the other inputs and outputs of the other neurons in your layer. Yes, sir?
Can the transfer function itself be nonlinear also?
So it's funny though, before the answer is the transfer function in this graph, and if you look at different books, that shows it different ways. This particular one, which I stole from this website because it kind of broke it out fairly well for the slide, it shows it as a transfer function and an activation function. In a lot of books, it would say a summation function and a transfer function, or a summation function and an activation function. There's not, as you go to different sources, there's not a universally accepted thing. I've even heard Andrew Ngee talk about, the frustration of not having an exact common vocabulary. So a transfer function and or an activation function is a little bit what the user says, but what has to be there is still the same. You're essentially summing all this, whether you want to call it a transfer function, and then you're taking it through one process, which says it might be a sigmoid, for instance. You're coming in and you're between 0 and 1. That's a lot of small networks will use that. There's a whole bag of different types of algorithms you can use for that. But you're basically putting that onto a graph where you have 0 to 1 there, and it's going to come in at some level, which gives it the weight of how important this neuron is relative to all those others out there. So I'm trying to give a non-technical explanation so that widely, but it's just math. It's not hard math, but it's just math. And we'll come back through, and there'll be some stuff on the backwards approach, because you go through, and so what you're doing here is you're going to end up wanting to update all those weights. So all those arrows between are weighted, and so as you go back, as you run through the network, the output is when you're doing the training, you're taking that data set, which is labeled. You know what it is. It's called supervised learning. I know what my output should be within my training data set. And as I start training examples through, I'm trying to get the overall error on that output to be close to what my known output is for the purposes of training. And so the idea here is you're trying to minimize the error in the network. So you've run it through like in the other, and you get to the output and you say, okay, well, I've got an output, and there's an error in it. Probably first time we've run it, it's probably a substantial error because all the weights we had set through here were randomized at first. So you end up with something, and you need an algorithm to take you back through to readjust all your weights to figure out what's my next iteration going to look like. And you're basically doing a bunch of iterations through this thing, trying to make adjustment until you get to where your actual output is what you're expecting your ideal, what you already know to be the case in your training data. It comes within a margin of error, okay? So the whole point of training is to try to get in that supervised training network to try to get your actual output within the margin of error of your known training output, what you already knew to be the truth going into the training for each of those. And so it might be, I'll make up numbers, it might be 95% if accuracy isn't too important to you. Maybe that might be fine for speech recognition if it's not a critical use case, for instance. occasionally you have to say something over again. If it's more a life and death kind of thing, it probably needs to be some, 99.999, however far out you want to go on that. And it varies on the use case. But the kind of the granddaddy approach to this, the one that was available back in 1992 to start with, it's called backpropagation. If you know anything about neural networks, you've probably heard about backpropagation. And what you're basically doing there is you're going back through with those weights, and you're going to say, I have to make a decision on how far of a jump to make from where I'm at to ideal as I go through there. And so you take a derivative of the output of each of those neurons, which gives you a how fast am I going to go there. And there's some biases that you can add in there and all, but the idea is you want to adjust each of those weights represented by the arrows so that eventually you get, I'll move it forward here. Actually, before I get to that, eventually you're going to get to what is a final network, which I'm going to show you in just a minute. So the point I'm making here is that you're basically doing a search. You're searching for the weights that give you the lowest global error for your output. That's what training a neural network is. You're trying to go through using techniques to adjust those weights so that when I give you new data to go through, I get the right output in a generalized sense, even if I've never seen that exact thing before. The network represents the right approach. And so that's what a trained network might look like. Let's say we got to an acceptable level of error in our network. Well, we stop because that's our threshold. That means we're success. When we get to that, making it up, 99%, because that's what we've decided is okay. We get to 99% accurate, 1% error or less, and we say, hey, that's good. I'm going to lock it in place, and now I can use it for the purpose that I designed it for. So that becomes a static thing. All those become constant, whatever those numbers are in that network. Any questions on that before I go on? I see some people kind of going, okay, and some people going, what the heck did he just say? You okay? Okay, so you're talking about essentially a nested hierarchy of concepts, which is what I kind of mentioned before. And if you think about, and when you're trying to do this thing where you're taking these concepts and you're creating abstractions based on the previous abstraction, based on the previous, if you think back to the layers that I was showing you, and you might have, I told you might have 5,000 layers for a substantial neural network. As it moves through, each of those layers is creating an abstraction from what it had in the previous layers. So as a use case, as a little one-off use case, if we're doing machine vision using a convolutional neural network, as you go in, you're first saying, I see contrast between light-colored pixels and dark-colored pixels. And then in the next layer, it says, oh, that's a line. There's a firm line there that I'm identifying. And that becomes the new feature into the next. And then you take that and it recognizes the shape. And as you put all these things together going through the network, eventually you say, hey, there's a face there with eyes and a nose and a mouth. But it's going through steps, feature by feature by feature, as it flows through the network to be able to generate that. And I have lost my thing. 1 second here. I may just have to walk to the laptop then and do it over here. So these are some really common architectures. I talked about a convolutional neural network, feed-forward, which was the example with backpropagation. Convolutional, think of as machine vision. That was kind of that one-off example I just said. Recurrent neural networks, there are a bunch of different types. The most common recently, although this is rapidly evolving, is called a long short-term memory network, and that's where the idea with recurrent is that if you have a sequence of things, like right now I am saying a sentence to you, and there is context and meaning in the relationship between those words, well, to know what, as the network is going through and processing that, knowing what happened in the last few bits as it came through, the previous word, is important for what the next word might be. So as you're analyzing that in speech recognition, for instance, different types of recurrent neural networks are commonly used for that use case because it gives you that time sequence. The convolutional is kind of doing a spatial evaluation. It's basically saying if you have a picture of someone's face, there's there is meaning there. I'm not random pixels that have no meaning. There's a relationship between every pixel to the pixel next to it, whether it be the edge of something, or this is showing the darkness in my eyeball, and all those are dark, and that right there in the pupil. There's relationship that is spatially represented, and therefore you can kind of cheat a little bit. You can say, well, recognizing the relationship, we can make that computationally a little less expensive by saying this region is represented. You end up pooling values and combining parameters together to make the computation less expensive. You could, in theory, do things like facial recognition with just a classical, fully connected backdrop, like in the example, but that would be a lot more expensive to do it in terms of the compute time. So the convolutional is kind of a subset that says, we're going to cheat a little and handle it a different way. The generative adversarial networks is really new in the last year and a half. The guy, one of the premier figures in the space, who also is the guy that had written the textbook that I'll mention in a few minutes, which is kind of the book in the space, created that, and that's where you're able to. You put two neural networks, and one generates results, and another one discriminates those results and tries to decide what's real and what's not. There's a bunch of different techniques and a bunch of different use cases, but you can actually have them battle it out to generate a reality. I'm going to show you an example of that in just a moment. It's really interesting. There's a lot of demo apps that show people a reality, and I say that kind of in air quotes, of things that have been generated by generative adversarial networks that don't exist otherwise. And I'm getting short on time, so I'm going to start moving a little quicker. That's the convolutional network, which I talked about before. Gives you the sense of you have an image, and you start breaking it down into those regions and reducing the number of computations you have to do to get it classified. Is that a car, truck, van at the end? And then let's get into the meat of what we're talking about here, and that's with Go. But there's one caveat I want to say. I think I said it at the very beginning. I want to reiterate. If you're working in another language that's not Python or C++, you have very similar issues as what Go has. And I've programmed in Java, C++, Ruby, a bunch of different languages over the time. These days, obviously Python, because that's kind of used heavily. And so Go has some foothold in this, but we want to talk about where it works and where it doesn't. So basically, we're doing a reality check. And if you know anything about Go, you know the Go tool, so I made up a pretend thing there. Go reality check. So Go is, if you've heard the messaging coming out of the Go core team at Google, they are branding the Go language as the language of the cloud. And that is, they've said, hey, we do really good. And if you think about Docker and Kubernetes and, a host of other popular solutions, and libraries that are out there are now written in Go. So it's a very popular cloud language these days. And they have, from a branding perspective, they're embracing that. So it's a pretty powerful language if you've used it. Is there anyone in here that's actually a gopher, a Go programmer? A few of us? Anybody else? There we go. So, do you guys? After having programmed in lots of languages, I love Go. It's simple, it's powerful, it's super performant, and gosh darn it, I want to use it in deep learning as much as I can as well, because I always feel like I'm regressing. I don't want to offend anyone, but I feel like I'm regressing when I go back to Python at this point. And so I'm looking for a Go-driven deep learning experience. That's what I want. We got the gophers in the middle building stuff out. I use Docker, I use Kubernetes. Both of those are written in Go, by the way. Kubernetes is now kind of the market leader in orchestration for Docker containers. If you don't know Pachyderm, it's kind of like Git for data. A lot of the things you would do with source code in Git or GitHub, you can do with Pachyderm. And it's written in Go, and it's kind of a Go community liked project. And I brought it into Honeywell for what it's worth. So it's a tiny little startup with like 8 people. But I fell in love with it, and we use it with our supercomputer, ironically. So here's one thing that you can do in Go. It's called machinebox.io. This is one of the, the team that does this are very, they really participate in the Go community. So you may have run across this in the past. It's a good approach. it's not a perfect approach, but I definitely would say if you're a gopher, you haven't gotten into machine learning, and you're interested in trying it, machinebox.io is a great way of doing it. I know a little bit about the internals, and I'm encouraged, and I'm not allowed to talk about it, kind of NDA type stuff, but they have some pretty cool stuff under the hood, and so it's a great way to get going, and it's free for developers, and they have a Go SDK, and it's fundamentally a Go solution, and so I encourage you to try that out. There's also Gorgania, which is one that I've played around with a little bit. I am by no means an expert in it. I'm going to run a quick demo real quick as we're talking about this. And so on the demo, I actually, when I talked to the gentleman who is the primary author on this, I've been traveling a lot. I'm in Atlanta. This is home for me, but I flew in last night, and I was like, dude, I'm not going to have a chance to try anything. So he kind of spoon-fed me an example to try out. So I'm going to do that real quick. And that is, let's see if I can get out of that. So he has an example here that is a character recurring neural network, and I could if anyone has any questions about what I'm actually doing, it's more I don't have enough time to cover that, so I can do that afterwards. I'm happy to talk with anyone, but this is a deep neural network that is starting to go through training that you will see up here. I'll leave it up. Oh, you can't see anything really, can you, on this? So, okay, so you can't see it because of the VGA, but what it is doing right now is running through training data and generating inferences, and what he's doing here with a recurrent neural network is he's looking at sentences. I think it's a book of poems or something, and he takes a line, and he starts predicting what the next thing is going to be based on what it's seen. And it's a cool, as a toy demo, it's a very cool thing. So I would say that along with MachineBox, there are other deep learning solutions, and this is purely an opinion. I don't want to offend any of the people out there doing this, but I would say either MachineBox.io or Gorgania are probably the preeminent solutions available to the Go programming language in the deep learning space. So I'm going to stop that, especially since you can't actually see it on the screen, and pop back. And I want to talk about Go in the ecosystem. And there's several things. So this is, as a gopher, and this is exactly how I see the world. I'm a gopher in the deep learning world, and this is what it looks like to me. I'm the gopher surrounded by snakes and little C++s running around. And I would like to convert those over, if I possibly could, and do more Go with it. So I'm the gopher. I'm Harrison Ford in Raiders of the Lost Ark. And I'm going to pretend that Cobra is the Python, but that's my expression every day. I'm like, why do I have to keep going back to Python for this? So, and that is partly because of some of the tools that I'm using, which I'll talk about a little bit. So despite being a dominant computer trend, we gophers are largely being left behind in this AI revolution in terms of Go language support for market-leading deep learning frameworks. So I'm not taking away from MachineBox.io, and I'm not taking away from Gorgania. Those are great solutions, but I'm at Honeywell, and I have a big NVIDIA supercomputer that I'm working with, and tons of data, and there's a lot of support that happens there, and the major frameworks that are where most companies are doing their work and most academics are doing their work, they have the support. NVIDIA supports those. There's a lot of tweaks and supports and adjustments that make it doable for you. But I don't have that in Gorgania because, as wonderful as the framework is, it's not big enough. It doesn't have the mind share, and it's going to be a ways till that goes. So it's too small, even though it's a fantastic framework. So I don't like that. And when I'm looking at these are the major frameworks. I might be missing one or two, but these are predominantly the major market-leading frameworks in the deep learning space. And anyone want to guess how many of those have Go support? That's right. There's exactly one, that has Go support, and that's TensorFlow. So, and TensorFlow is a wonderful framework. It's you can certainly bike shed what's the best framework, and everybody has their own opinion and all that, but it's the market leader currently. It doesn't mean it's the best. It's the one that we use at Honeywell because it's the market leader, and if I want to go out and hire talent to do this, That's where I can find it most likely. I can also find Keras, I can find Cafe, I can find some of that, but when we standardized, we went with what makes the most sense from a business standpoint. So the problem there is that you're looking at Hello World, right, and you can't see it really. When you back up, can you read that code at all? Is it not legible? Okay. It's this we're on VGA here, so it really runs the image. So normally on most screens with HDMI, you can see that clearly, and you would see Hello World for Go. And the one thing you can read here, which is really the important thing, is that this is straight out of the TensorFlow documentation. That's verbatim quote. Is that it's really for loading modules, not for creating them. So what TensorFlow's current take today is hey, take our great tool that's driving all the Google services, it's open source, we want you to do it, and you can run a model in Java, you can run a model in Go, but hey, you're going to build models in Python whether you like it or not. Python is the primary first-class interface, though TensorFlow under the hood is actually written in C++. Python is the primary interface. That's how they intended it to be. And so it's great. I mean, if I want to go deploy into a product, I can use Go. I can wrap it up. I can either wrap the model in Go and run it, or maybe put it in a Docker container, which is what we usually do if we have that option. But at the end of the day, I can't do my training that way. I cannot have a Go ecosystem. And as a devout Gopher, I don't want that. So, I said we're in the Wild West for deep learning right now. This is for deep learning, this is the equivalent of when the internet was coming into being. We're in 1994 right now for when the internet was coming into being, and standards were still being developed and things were changing. Well, that's how deep learning is right now. There's really a lot of variability. There's a lot of books coming online. If you go to O'Reilly or go to PactPub or whatever, there's a whole bunch of deep learning books. But we still, and I would argue there's a reason for this if people are honest, there's not one that says deep learning best practices. And and deep learning design patterns and such as that. And every other programming language out there has tons of those. And that's because we're still figuring that out right now. And I would argue that if anyone came to me tomorrow and said, hey, I just wrote deep learning best practices, you are so full of it, because you may say that, but the next guy or next lady is not going to agree with you. The best we have are some kind of generalized rules of thumb that we go forward with right now, but they haven't codified into that. So this is a call to action to Gophers. And that's, I first did this talk at GoLang UK, which is one of the biggest conference in the UK for Gophers. That was in London a few months ago, and a lot of the name for those of us who are Gophers, like every programming language has the people that the people that are kind of the leading people. A lot of those people were there, and I wanted to say, get on board or we're going to get left behind. We love this language. We think it's better than so many others. And if you want to believe that, and if you have that bias, then do something. I would argue those of you who are Java programmers, I would argue the same thing. You can use TensorFlow in terms of running a model, but you can't actually do the training on it. So if you want to do something about it, do it now. And I want to talk a little bit about that. So we need fully functional Go APIs in all of the market-leading frameworks. Certainly, my focus is TensorFlow, but if you're in any language that's not there, and you don't want to get left behind, this is the fastest moving train I have ever seen in my technology career. So, I've been a career technologist. We've been racing up the curve on all these different technologies. Think how fast Docker came into things, if you know that. This is speed-wise, this is blowing all that away. So we need to make it happen. And so it's up to us. And so I have been in this conversation for several months with the team, the core team at TensorFlow, about how we get this happening. This guy named Asim has been working with me on a roadmap. Now, the roadmap is in development right now. It's not released yet. It is going to be a roadmap for any developer, Go, Java, anybody out there who wants their language to have much better support for TensorFlow. But we're organizing folks in the Go community to chip in as an open source project, chip in terms of effort, and start writing against the APIs that they're going to provide for us, their C APIs. So if you're Go, the downside is that requires CGO, which I know we don't like. It's a distaste, but it's better than nothing at all. And that gives us, in theory, if we want to write it, we can get full access to everything TensorFlow will do. And so we're trying to bring it up to full parity with the primary Python interface. If you're interested in that, please contact me afterwards. And so I wanted to say one other thing. I'm going to show you a graph that you've seen before. You may not have seen it for deep learning, but you've seen it for others. It is the hype cycle. You'll probably recognize it in just a second. But it's a story that the initial thing is not so good, but going beyond that, I think there's a really big opportunity to catch up here. And that is this. You've seen this graph, it's used all sorts of technologies. Every technology out there, Gartner puts it on it and shows where in the life cycle you are. And basically the idea is that every technology has its hype phase first, where everyone's like, oh my God, this is the greatest thing on earth. And you get to the pinnacle, which is where deep learning is right now, according to Gartner, in July of this year. And then basically they've oversold it. They've said, oh, this thing, whatever this thing is, Docker, deep learning, Java once upon a time, it doesn't solve every problem you could possibly have, and people get frustrated because they try to use it for problems it doesn't. And they plunge into the trough of disillusionment. That's what it's called here, if you can see that. And then they kind of go, okay, well, our expectations were too high, so they push it back up. Almost out of time. They push it back up into the slope of enlightenment and the plateau of productivity. And so what I'm saying is, you know what? If we're just about to go into a time where we have to play catch up on deep learning because we have to play catch up to get in the game, and a bunch of other people are saying, we don't want to invest money, we don't want to invest time, we're frustrated with it, and we go through a period of months or a year or so where people are kind of pulling back, I would say Gophers or Java people or any other people out there that want to do this, jump in and make it happen while people are frustrated, so that when we come out of that and we're coming back out, if that actually happens as predicted, that we're kind of on parity at that point. This is the textbook. It's the authoritative textbook on deep learning. It's kind of you could argue whether it's graduate or undergraduate level, but it is a mathematically rigorous introduction to deep learning. It just covers the major architectures. There's lots of stuff in deep learning it does not cover, but it is it came out a year ago. It's already somewhat out of date because the field is moving so fast, but for learning the basics, it's the place to go. Elon Musk is doing his little thing there from when as co-chair of OpenAI saying, hey, this is a great book. So I would encourage you, if you have an interest in this field, to get that if you don't already. And then the final thing, since we have maybe a minute, I'm going to run over, is I want to show you a demo real quick is the last thing we're doing here. And this is not about Go. It's just about deep learning, but it's a really cool thing if you see what's... So this is the US military. This is a test over the Nevada desert that happened a little over a year ago. This video was released this past January. These are F-18s in the video. Pardon the mouse pointer that's there. And so you're about to see them dropping little dots. It'll have a zoom in just a second, and you'll see little dots, black dots, falling out of the F-18s here. And the little dots that you're going to see dropping out are drones. They are military drones, and I think it's just about to show you that. And we get the zoom in now. And see the little, are you able to see on the screen that there are little blips of dots going through? And so those are drones being dropped into the airspace. And it's about to go then to a digital display that the testers are using. And I'm going to show you what's happening as we go through this. But it's pretty amazing. So the actual physical drones that dropped out of the F-18 are the green things. The red things are imaginary targets that are being painted with radar into the space. They don't exist. It's only on a radar screen. And the drones are flying around via radar, targeting these fake things for purposes of tests. Now, here's the thing. There's no human being running this. Those drones, all those green things, dozens of them, are self-organizing drones. It is a swarm. It is a self-organizing swarm. And what the testers are doing is that they are making the targets go through different configurations, and the drone swarm self-organizes around every configuration in real time. And remember, the green things, which are not colliding, are real. They're flying in the air above the desert. So they're aware of each other, they're aware of the targets, and they're dividing and conquering the targets. And as they go into these, as they radar paint these different things, They adjust their configuration and fly around to attack. This, even though this is a tangent, this is the future of warfare. This is a common deep learning approach. This happens to be a military one, but there's functions like this that you could do in commercial aviation. You could do it in almost any industry you could possibly think about where you're applying this. And this is a picture. You can't really see it because of the VGA, but if we had HDMI coming out of there, you would actually see a bunch of little dots flying around in real time, which are the drones. There's nothing target-wise there in real life, but they're organizing, they're circling around. You saw that single dot where they did their single red dot and they were circling around? It was showing them circling so they can each attack it. So this is deep learning in practice for a real military purpose. So, you know, that's just one thing, but it shows you that's pretty powerful. And this is old stuff. This is the stuff the Pentagon releases to show you, hey, look at cool stuff we're doing. This is not the secret stuff that goes on. And I'm not going to speculate on what secret stuff is. I'm just saying that's pretty amazing when you think about it. And if you think just within the warfare context about anti-personal, anti-tank, air-to-air, there's a lot of different functions for this. But you've heard about drone swarms. Well, these are real-life drones by the U.S. military. This technology, military or commercial or any other use, is not going away. And we're going to see it for the rest of our lives. And that's one of the reasons that as a gopher, in the context of Go, I want to get in on this now. I don't want to be doing Python for this for years to come. I want to be doing it as a gopher because I like the language, and you Java people, I'm sure you feel the same. Once upon a time, I was one of you. So that's it for that. That's it.